So thank you for staying that late. I will be presenting part of my PhD project. So the title is the Watershed Tungsten Deposit, and it's a Permian metamorphic tungsten upgrade after a Carboniferous magmatic-hydrothermal mineralization event. So I will be showing mostly whole rock geochemistry to understand the footprints and the fingerprints of the deposit, as well as trace elements in scheelite to understand the origin of the mineralization. So Watershed is located in northeast Queensland, about 100 kilometers northwest from Cairns. And it's one of the biggest undeveloped tungsten deposits outside of China, with about 70,000 tons of tungsten trioxide. In terms of regional geology, Watershed is located in the Mossman orogen in the northeast there in yellow. And the Mossman orogen is interpreted to be an ancient forag basin. So Watershed is located here in the central part of the Mossman orogen, and in this part the rocks consist of strongly deformed metasedimentary rocks of Ordovician and Silurian age. And these deformed metasedimentary rocks are intruded by the Kennedy Igneous Association from its Carboniferous to Permian event. And specifically, Watershed is surrounded by the Waipala supersuite. So other important deposits in the area are the Mount Carbine tungsten deposit and the Wolfram Camp tungsten deposit farther south from Watershed. So zooming into the deposit, the rocks that crop out in this area comprises mostly slate and slate siltstone breccias and sammites from the Hodgkinson Formation, and also scar and altered conglomerates in this area. So these metasedimentary rocks they have a very linear north-northwest linear fabric, and they are intruded by granitic dikes and also with scarcely dioritic porphyries. Those are Permian in age, and these red lines are a long section and a cross section of the deposit, or the traces. So this is the long section there, showing the upper right in AB. So here we can see that these rocks are very, very deformed. This deformation of these rocks are regarded to the first three deformation events, which are more ductile, D1 to D3. And these rocks are here intruded by these Permian granitic dikes. And these red lines are the vein zones. And these veins were intruded during the Permian, and they comprise more a brittle-ductile deformation event. And these symbols correspond to the locations of the samples that were taken for whole rock geochemistry. Okay, so this is the cross-section there in CD. Here, because this is orthogonal to the main deformation trend, then we can see here that this deformation is very tight, with very tight anticlines and synclines. And these are intruded by monsonitic dikes that were dated at 350 million years, and they are Carboniferous, and those are very enriched in scheelite. This is kind of the first mineralization event during D1 and D2. And also here we can see some of the samples that were taken in this cross-section. So this is an outcrop map that it's where the yellow star is. So here we can see that these are the scar-altered conglomerate, and the gray are the slate and slate breccias. So we can see that scheelite mineralization here in yellow they occur mostly in veins and in shear zones. So it's a very similar to orogenic gold system that mineralization is related to brittle-ductile deformation. And this corresponds to a paleostress analysis, and we can see that the main paleo regime at that time in the Permian was a compression from the east-west and with an extensional regime in the north-south orientation. So the main ore mineral is scheelite, which is it's color blue under UV light, and we can find scheelite in veins and vein halos, in skarn-altered conglomerate, and in monzonite. So this is how it looks. The scheelite that occur early in the history of watershed during D1 and D2. So here we can see that scheelite is disseminated in monzonitic dikes. This is the Carboniferous in age, and here we can see scheelite that occurs in skarn-altered conglomerate following the D1 and D2 foliation. So there is a late stage scheelite mineralization event that this is related to brittle-ductile deformation during D4, and this occurs in stringers cutting skarn-altered conglomerate and also in veins. The veins were dated at 275, which is Permian, and this shows like the very complex paragenesis of these veins, where an early stage of platch scheelite and minor quartz occurs in the margin, and then there is further opening with a later quartz event. Also, we have some calcite and pyrrhotite event. That's very late stage. It's a classic paragenesis of tungsten systems. And here in this image, we can see that veins, D4 veins, they develop very well in skarn-altered conglomerate, and when they encounter slate, then they pinch out. So that's very indicative of like this form in a deformational regime, where the rheology of the rock plays a very important role. So this is a backscatter image showing the relation between scheelite and platch in veins during D4. So here we can see the most important thing here is that, so this platch over there, we see over there those red dots, they have a more anorthitic composition. It's more calcium rich, and then when it starts to develop or grow, then the later stages of the platch, they shift into more albitic composition, more sodic composition. So possibly this is showing that the calcium of the system was incorporated in scheelite, leaving the platch more depleted in calcium. So this is another image of the skarn-altered conglomerate, a backscatter image, showing how clinozoisite from D4 is replacing garnet from early D1 to D3 garnet. So also this replacement is very important, because when you have this replacement, then clinozoisite needs less calcium, so possibly liberating calcium to form scheelite as well. So all these relations can be put together into the paragenesis table. So the main important thing here is that we have scheelite here in light blue that occurs in monzonitic dikes, in skarn-altered conglomerate, and in vein, and in the intrusives and in skarn-altered conglomerate, they occur during peak metamorphism, which is like a upper green schist to lower amphibolite fascia. And also we have a second event during D4, during also the retrograde stages, basically, that occur also in skarn-altered conglomerate, and in vein, together with plagioclase. And the important thing here as well is that scheelite in skarn-altered conglomerate occurs together with clinozoicite. So to analyze the footprints and the fingerprints of watershed, samples were taken from vein halo, and skarn-altered conglomerate. That's the relation that we always see, the vein with the skarn-altered conglomerate, and the vein halo that is kind of an altered version of the skarn-altered conglomerate. And also we analyze samites, that distal samite from the deposit here in purple, as well as proximal samite that were taken within the deposit. And also samples were taken from intrusive rocks, the granites and the diorite and the monzonite. So yeah, this is a bit crowded, but basically what is showing here in the y-axis is the set score of the central log ratio of all the elements, and the elements here are grouped by similar behavior among different rock types. So the main important thing here is that in this side we have veins and monzonite, and we can see that veins, they have a totally different behavior in terms of geochemistry compared to the host rocks. So this is vein halo, skarn-altered conglomerate, and samites. So here, for example, we have that the ore elements, which are the ones that come with the veins, are enriched in tungsten, rhenium, moly, copper, scandium, boron, and beryllium. Here above the zero are enriched. And the other important thing here are these skarn elements that are enriched obviously in skarn, but they are depleted here, more depleted in vein halo. So possibly showing that these elements were incorporated into the veins to form all the mineralogy in the veins. So also we can see that rare earth elements, they have a very different relationship compared to the host rock. We can see that in most of the cases, the heavies in more kind of warm colors are more enriched in veins compared to the vein halo. So possibly showing that all those heavy rare earth elements are being incorporated into veins, so scavenged from the host rock into the veins. So also from these spider diagrams of rare earth elements from the different host rocks, we can see that veins here in letter B they have a totally different pattern compared to the skarn-altered conglomerate and halos and samites and the intrusives. So that's very important. So jumping into the trace elements in scheelite, we can see that the scheelites from different textural position and the formational events from D1 in monzonite and skarn-altered conglomerate, they have different patterns compared to the late D4 scheelite in veins, vein halos, and in skarn-altered conglomerate. So because of these differential patterns, if we plot all our trace elements in scheelite into this ternary diagram of like light rare earth elements, medium rare earth elements, and heavy rare earth elements, we see that they plot in very specific zones. So the blue are the scheelite in monzonite, the greenish are in skarn, and the red in D4 veins. So we can see that here this light blue area are the scheelite from the literature that are intrusive related. So they plot fairly in the same area. And also this green are the scheelite from the literature from skarn. And also this yellowish are the scheelite that occurs in orogenic gold system associated with gold mineralization. So with this, we can deduce that the scheelite from the monzonite are intrusive related scheelite, and also the D4 scheelite from veins are regarded to metamorphic fluids. similar to the ones in load gold scheelite. So also, seeing like all the four bottom diagrams, we can see that the scheelite, that we can differentiate scheelite in terms of ratio of elements, and also depending on some trace elements. So, for example, the scheelite from monzonite in light blue and skarn in green and yellow, they have higher strontium in their crystal lattice compared to the one in veins. So that also can show us that there are different discriminators to characterize the scheelite, as well as these ratios, which is expectable because of the different rare earth spider diagrams. And then on the two top diagrams, the one on the top left, this is the europium asterisk normalized versus europium normalized. And if the scheelite plots on the line, it means that they are more enriched in europium 3+, which is more oxidized. And we can see that the monzonitic scheelite and the skarn scheelite, they plot along mostly along that line, compared to the reddish, which are from veins, which is more enriched in europium 2+, which is reduced. So we can see that there was maybe a shift from more oxidized conditions into more reduced conditions in veins, possibly because of the interaction of the fluid with very reduced rocks like shales and all those host rocks that occur at Watershed. And this is in agreement with the moly content of the scheelites, where the more moly the scheelite has, is more oxidized. So the moly from the monzonite and the skarn, they have relatively higher moly content. So also this shows similar trends, that we have a shift from more reduced to from more oxidized to more reduced conditions. So some concluding remarks. We have that the ternary rare earth element plot for scheelite differentiates very well the different scheelites at Watershed. And also here we have to keep in mind that it's very important to check through petrography if we have any other kind of late alterations, so that you may have different or some scheelite plotting in different spots, but that's very important prior to use this ternary plot. We also have that the redox conditions from scheelite from D1 and D2 are more, they were coming from more oxidized fluid compared to the late D4 scheelite that shift into more reduced conditions. And then we have that the hydrothermal fluids that introduce tungsten, they also introduce beryllium, boron, scandium, copper, and moly, and rhenium. So that's kind of the fingerprint of Watershed. And that these fluids also leach some rare earth elements, neobidium, calcium, fluorine, phosphorus, iron, and strontium from the host rock into those veins. And the regional footprint of Watershed preserved in samite include tungsten, copper, moly, calcium, iron, manganese, and lithium. That's on approach in Watershed. And that's all what I have for today. Thank you.